Test, test. Audio okay? Good morning, ladies and gentlemen. My name is Daniel Skuka. I work for the ESA Communications Department. Welcome to the European Space Operations Center, part of the main ESA location here in Germany. We're also located in Cologne with our astronaut center. And today we are here to present to you the results, the images, and an update on our Hera mission and the flyby of Mars, which took place yesterday afternoon. And our science teams, scientists, many of whom are here in the room with us, were working until very late to get the images processed and to prepare a selection for release now. I would just like to remind everybody that the images are under embargo, please, until noon today. We will publish them on our website and our channels starting at noon. We'll also reveal them to the public in a live webcast, which will be going out via the ESA YouTube channel also starting at 12 noon. So I would ask that you don't publish any of these before 12. Before we begin with our formal running order of speakers, whom I'll introduce in a moment, I would absolutely like to ask Holger Krag to say a few words. Holger Krag is the head of our space safety program based here at ESA in Darmstadt. Holger.
Oh, you don't, I don't think. Yeah, thank you and good morning, everyone. Welcome, scientists and journalists. This is the European Space Operations Center, where 30 of ESA spacecraft are operated, and one of them is Hera. That's why we are here today. Now, asteroids, they have been a risk to life on Earth, basically since life exists, and this is a risk that is still imminent today. So 38,000 asteroids are being tracked and monitored very closely. 1,800 of them make it to the risk list as of today. And just recently, I'm sure you haven't missed it, there was a very close call with 2024 IWAR 4, which reminds us that this risk is still there. Now, asteroids larger than 1 kilometer, I think they're fairly well known, but asteroids, when it comes to a few tens to hundreds of meters, they can surprise us basically every day. And an example everybody remembers is Chelyabinsk 12 years ago, a total surprise. But asteroids, a bit larger than that, 100 meters, they would cause damage where even evacuation would not be an option anymore. So here, deflection is the option to choose. And now we are getting closer to the topic of Hera. We need to go into space and deflect them. In 2019, ESA has set up the space safety program, which is meant to protect us from the hazards coming from space. And as part of this program, we have put up a very ambitious planetary defense line with two very clear goals. By 2030, we want to find and get pre-warning for all asteroids larger than 40 meters with the pre-warning time of 3 weeks. So in other words, getting in a situation where we can do civil warnings and evacuation. And we want to get ready to deflect asteroids of 150 meter size, exactly the size of objects that we are aiming towards to with Hera. Hera is the first mission coming out of that program. It was built in just 4 years, which is for a space mission very short, and which shows also our ability to really react fast. It will enable the deflection of asteroids in space by inspecting the target. Before we go for the deflection action, we need to understand what the target is about: the mass, the dimensions, the composition, and the asteroid type. This is what Hera will do. Overnight, yesterday, Hera has passed its first solar system body, Mars, together with Didymos. And the imagery we received yesterday is just astonishing. You will see it in a moment, and they demonstrate the full success that Hera is. With that, today, I think we have proved that Europe is in a position to contribute an important capability to the global efforts of planetary defense. But we will not stop here. We will set up several telescopes on ground. We call them Flyby telescopes for a complete network by 2030 to provide us the early warning capability. And as we speak, the team is already implementing the next planetary defense mission, Ramses, launched or scheduled for launch in 2028, aiming at asteroid Apophis coming very close to Earth at 2029 and accompanying it during its pass through Earth. So these measures will bring us very closer to our planetary defense goals and will be proposed to the ministers of the upcoming Ministerial Council in Bremen in November this year. This will be a very decisive moment for all our planetary defense action plan. But with that, I think we can be a bit bold and we can say that maybe in a few years, the generation sitting here will be the first one that actually has a response to this problem. And I think this is quite an important action. Now, allow me to close and get to the real stuff by saying some words of appreciation. First of all, Jan Candelli and his team in ESA and in industry for doing the impossible possible. Patrick Michel, on behalf of all scientists sitting here, for pushing for the mission, and all our member states for actually making this mission possible. Thank you. And now back to Daniel and the real stuff.
Thank you very much, Holger Krag, who is the head of our space safety program here at ESA. And before we carry on, I'd just like to cover a couple of logistics points or scheduling points. We will present to you this morning a little bit of what's happening with the Hera mission, a little bit of where we are, how we got to Mars, where we're going after yesterday's flyby. We'll present to you, of course, a selection of the images coming from the 3 imaging systems that were active around flyby. And we will also ask our planetary defense specialists to provide an update on what Holger mentioned, the recent very close approach of, or not close approach, but discovery of asteroid 2024 YR4, which will make a close approach. And of course, to talk a little bit about some of our other activities happening in the planetary defense domain of our space safety program. It's a very cool topic. When we're done our formal program this morning, there'll be an opportunity for questions. So please, if you have a question, just keep it in your brain, and then we'll pass around the mic. We've got some catch mics, and we can do a very full question and answer session. Also, our experts are available for interviews, one-on-one interviews, which you can do here if you wish. We can also host any shootings or any interviews you want to do in our main control room, which is not being used today for simulation training, as we have another launch coming up very soon, biomass. So that's available for us. And I'm sure if you want an interview, I'm sure we'll be able to find a place and an expert speaker who can talk with you. Holger mentioned the Hera science community here with us. Just to point out some of the people in the room that you may wish to speak to, of course, is our very special guest PI, Principal Investigator, Dr. Brian May, who is one of the co-founders of Asteroid Day. That's a very long-standing celebration here in Europe where we talk about the risks of asteroids and planetary defense. And he, of course, is working with our scientists. He's an astrophysicist as well as a fantastic guitarist. I also want to point out that we have in the room a number of colleagues from the ESOC Center. We have Holger Krag. We have colleagues working in mission operations, colleagues working in flight dynamics, colleagues working in all the various specialty areas. So if you want to find out anything about what we do to fly missions here at ESOC, please don't hesitate. And we should be wrapped up here in about an hour, and then we'll do the individual interviews, and then we should be done by noon. If you have any questions, please don't hesitate to contact me. My colleague Bernard van Beyer, who is our media relations officer for here in Germany, please don't hesitate to contact him. My colleague Simona, just sitting in the corner, of course, don't hesitate to contact her. And indeed, just ask any of us, and we'll do whatever we can to help you out. Good. With that, I would like to begin the formal portion of our press briefing, and I would like to ask Michel Kuipers to come up on stage, and also Patrick Michel. and if you want to go both together, if you want to go one at a time, and I'll pass over to you, and you can take five or so minutes to give us
Okay, thank you very much.
Michel Kuipers is our mission scientist for the Hera mission, and Patrick Michel is our primary principal investigator leading the science team, which involves scientists. I think I would almost say all over the world, but you'll give us details. Thank you.
Okay, good morning, guten Morgen. We'll first start with giving an overview about the Hera mission as such. So, Hera was launched in October last year and is now on its way to asteroid Didymos. And we are here essentially to celebrate the successful Mars flyby from yesterday. And we will start a little bit, if we get the slides, with an overview of the Hera mission itself. So Hera is a medium-sized spacecraft that is now on its way to the asteroid. And something really special about the mission is that it has two small CubeSats with it. So those are roughly 30 times 20 times 10 centimeters small spacecraft. Oops. Oops. No, it's the wrong one. Oh, it's the right trajectory, yes. No.
Fortunately, the flyby went well.
Yes, yes. Okay.
Oh, okay.
Okay, let's give it a try. So I was talking about the CubeSats. And yes, actually the CubeSats, in this model we are already at the asteroid. The CubeSats were in here and have already been released at this point. And we will, and to give a little bit of background, Hera is part of a cooperation with NASA, which is called Asteroid Impact Deflection Assessment, or AIDA. And in this context, the NASA's DART spacecraft impacted Dimorphos, the moon of asteroid Didymos, in 2022. And now the overall objective of the Hera mission is to see what happens there, essentially, to determine the mass of Dimorphos, to know how efficient this impact was, and generally to characterize the asteroid, to be able to extrapolate the output if we would need it one day. As was already mentioned in the introduction, asteroids occasionally hit Earth, and we want to be prepared, and with those missions we would like to demonstrate that we are capable of deflecting an asteroid should we need it. Should we need it one day.
Just a test who didn't switch off the cell.
No, it's no alarm on my phone. I don't know what it is. Maybe once this noise stops, you can continue a bit about the science.
What's going on?
Now I really have something on the phone. Oh, yeah.
Ah, this is from the...
This is an emergency alarm. I haven't even looked which kind of emergency.
You can just
just say
Yeah,
it's a Hessen regulation. They just do an emergency.
But it's
Ah,
only,
okay.
it's a
It's
test,
just a
right?
test.
Okay, so it's an ESA regulation, and it's just a test.
It's actually not
It's
an
not-
ESA
it's a
regulation.
Hessen
It's
regulation,
a
it's a
Germany-wide
test.
test.
Germany-wide
Yeah.
test.
Please
Exactly
press
when we want to do
Please
this.
press OK on your mobile phones to switch off the emergency alarm. Now it's there.
Okay, so now you want to describe?
Okay, yeah, this is pretty much what I just said without slides. So DART hit in 2022, and DART also had a small cube that looked at what came out. It's essentially the material that was ejected from Dimorphos, and Hera with its 2 CubeSats will arrive late 2026. And I think... I'm sorry, this doesn't... Okay, I just hand over for the scientific part to Patrick now.
Okay. Thank you, Michael. Okay, so the point was to show you how Didymos and Dimorphos look like before, but actually, since we don't know what it looks like now, it can be seen here, if you want. And in fact, the good thing with this mission is I think it's the first time that we have images of a celestial body which will not be the same when we arrive. You know, we have several missions that go to the moon, to Mars, and each time we go, we learn something, but it's still the same body. Here we have superb images by DART before hitting Didymos and Dimorphos, which show us, you know, boulders, etc. And we already know these boulders are not there anymore. So we don't know what we're going to see. And the whole operation of yesterday, the Mars flyby, was in order to put us in the correct trajectory to go to Dimorphos. So that's absolutely fantastic, because in 1 year and a half, we'll discover basically a new body, which is the same as before the DART impact, but DART made something that we tried to predict, but we're not sure. And therefore, I think this is really fantastic, because that will help us to really understand the physics of the kinetic impactor and make it a reproducible technique if an object comes to us. So unfortunately, we don't have the images of Didymos and Dimorphos. Here you can see that in principle, this is what you're going to see. I can already tell you this is wrong. And probably what we predict is also wrong, as always, because I don't expect such a small crater on the surface. What we think now is that we entirely reshaped this asteroid because it was very weak. And this is the only way we have to explain the data we have from DART. But I'm very humble because some of us and our great science team who is here already experienced each time we went to an asteroid, we were surprised and we were wrong. So probably this time we'll have, again, a lot of surprise. So I cannot wait. I really thank the project team that made us launch in due time, 7th of October 2024, great souvenir. The operation team that made this successful operation yesterday, and we pushed them because of some of us, we asked them to also observe one of the moons of Mars, and that was not planned initially, but you know, scientists, if you ask them something, they have no limit. So we wanted to do this flyby, not only an operational thing, but also something from which we can extract science, and we're going to see that in the next presentations. So I really want to thank all the people who worked. I know the industry is also who did the spacecraft, because this is absolutely amazing that ESA could, you know, develop this mission in 4 years and already have this flyby and all images down. So this is fantastic. And now we are all looking forward to what will Dimorphos and Didymos look like. So I now pass the voice to the mission analyst, I think? Yes. Yeah? Okay, thank you very much.
Thank you, Patrick and Michel, and Michel Kuipers. And now I would like to introduce Pablo Munoz, working on our mission analysis team here at ESA within our flight dynamics division. So, yeah.
Thank you. So good morning, everybody. So I was mission analysis lead for Hera, so taking care of designing the trajectory of Hera, and I would like to discuss today a bit how we get to an asteroid. Let's see if this works. No. Ah. Thank you. So if you can pass the slides then, thank you. Okay. So first we have this video that we prepared for the launch of Hera, and then we can fly along with the mission. So it started on October 7th last year when we launched from Earth. This was a very high escape velocity from Earth launch because we need that to reach the orbit of the asteroid. Then a couple of weeks later, we performed the first deep space maneuver where we switch on the engines of the spacecraft to get an increase in the velocity, to target also the swim by of Mars. And then we have the swim by of Mars yesterday, which we use to we use its gravity to get a kick, and then this push changes the trajectory of the spacecraft with great benefits because we save a lot of fuel. Then in February next year, we'll have another deep space maneuver to target the encounter with the asteroid, and then we start what we call the rendezvous phase, in which we perform a sequence of braking maneuvers to align the velocity of the spacecraft and the asteroid, and then we can start the proximity operations in the binary asteroid system. Let's see if this works now. Yeah, good. So now we have this is a typical engineering plot as an outcome of the trajectory design, and here I have labeled the milestones, and I would like to use this plot to just discuss a couple of nice ideas about how we get to an asteroid. So first, we see in black the orbit of the asteroid. It goes beyond the orbit of Mars, so it's very big. That's why we need a high velocity at escape from Earth to reach it. And not only we need to match exactly the orbit of the asteroid around the Sun, we also need to have the proper phasing, such that the spacecraft and the asteroid meet at the same point. And since at launch the Earth was ahead of the asteroid, we need an orbit that is higher than the one of the asteroid such that it takes longer to perform a revolution around the Sun. And in the meantime, the asteroid catches up, and then we can meet essentially one revolution later. So this we achieve with the velocity increment provided by the launcher and also by the execution of the Deep Space Maneuver 1. And the Mars Swim By and the Deep Space Maneuver 2 take care of rotating the orbital plane, essentially, or mostly, rotating the orbital plane to match the one of the asteroid. And the last slide, so this is just the trajectory that we flew yesterday as it was designed essentially 1 year ago. So we approach from the right side of the plot. So this is essentially from the Sun direction, which is very beneficial for the illumination conditions, so we can observe all the illuminated, almost all the illuminated surface of the planet and Deimos. And we first fly by Deimos, so we take observations at around 1,000 kilometers. And this was designed such that Deimos would be observed in front of the Mars disk. The idea was, or basically crossing through the Mars disk, the idea was that it was very important for calibration of the instruments to have observations of Mars. And by doing that, we do not have an outage. While we have to look at Deimos, we would lose Mars. But with this design, we have always observations of Mars throughout the whole flyby. Then we have the closest approach at 300 kilometers, but at that time, the spacecraft is not looking at Deimos anymore because it moves far away outside of the field of view of the instruments. Then we have about 40 minutes later, we have the closest approach to Mars at about 5,600 kilometers altitude, and a relative velocity of 9.3 kilometers per second, which is really fast. And the other point I wanted to mention with this plot is that you can see slight bend of the trajectory as we pass around the planet. It's not very big, it's just 7 degrees, but this is exactly what we use to change for free the velocity of the spacecraft, both around the planet in direction and around the Sun. And this 7 degrees is equivalent to more or less 1 kilometer per second. And just to give a context, this is essentially all the fuel we have on board the spacecraft. So this is really a great benefit for the mission, this Mars Swimmer. And that's all I had, so thank you very much. I pass to Charlie.
Thank you very much, Pablo Munoz from the mission analyst section here at ESOC. I would next like to ask our Hera spacecraft operations manager, Charlian Gubruz, to come up.
Good morning, everyone. I'm the Hera Spacecraft Operations Manager, and I would like to give you a short briefing on the status of how the spacecraft behaved and acted during this flyby, and what were the challenges and the outcomes that we have achieved, basically. So, as shown before by Pablo, the trajectory of the Mars flyby was a very fast one. We flew by with 9 kilometers per second, and this ends up in two challenges for the spacecraft. First of all, we have a very short duration for a flyby, so a window of an hour or half an hour where we can take the images of Deimos, Mars, and Phobos. And another challenge is on the spacecraft is the high dynamics that we have to exercise. So the spacecraft is flying by very fast, and at the same time has to rotate in order to keep Mars in the field of view, but also be able to point to the objects and have a still and performant pointing so that we can take nice pictures. So that's one challenge. The other challenge is that here in this, for the first time, Hera exercised that all the cameras on board are operating at the same time with an extremely high load on the spacecraft, which has a lot of load on the computer and on the storage of the images. So these were the challenges that we were facing. And this is also very much representative of what we will be operating where we are at the asteroid and flying by the asteroid system. So many images taken at the same time. So long story short, these were the challenges, and the spacecraft behaved very well. It exercised what it had to do extremely well, and we are so happy. Approximately 600 images were taken in this window, spread amongst 3 of the instruments, and the initial analysis of the orbit says, as shown by Pablo before, that we are on track to the asteroid system. So yeah, this shows that, again, Hera showed that within a window of 2 months, so right after the launch of Hera mission, we started preparing the Mars flyby with support of industry, validations that we performed on ground with the engineering model and in flight that resulted in this success of this flyby. And that was not all that we did, so we even took it one step further, as we like to do it on Hera. We have on Hera a special mode which we will need to use when we're at the asteroid system. So when in the asteroid system we are very close to the asteroid, the field of view of our cameras will be fully filled with the asteroid. So this means it is difficult to navigate under these circumstances. For this purpose, our partners have developed an experimental mode, a technology that will be demonstrated by Hera when we are at the asteroid called so-called future tracking. So what will happen at this point is that distinguished features, now in this case on Mars, will be tracked, and their relative movement will be checked from image to image, and based on that, Hera will be able to keep pointing to Mars or asteroid. And this is something that we have exercised during this flyby, and the first results of that also show that we are ready to exercise this at the asteroid system. So this was a unique opportunity. We wanted to not let go of it and use this opportunity to validate something, because when we're at the asteroid, there will be no time for mistakes and no time to validate because we have such a short mission of 6 months. So summing up, the Mars flyby went as planned, but there was a lot of work behind that, and thanks to all the industry partners and partners here at ESA that supported this. And so yeah, what comes next? In 1.5 years from now, we'll be at the asteroid system. The spacecraft, in the meantime, will be equipped with 3 more units. 2 of them, one of them is another camera, one is the altimeter that we will be using when we're getting very close to the asteroid. And these things are being prepared on ground, uploaded to the spacecraft. So here the flight control team is preparing this in advance. And in general, the overall operations around the asteroids are being prepared. So what does that mean? Now we have 1 spacecraft to operate, but at the asteroid there will be 3 to be coordinated with, operated by different parties. And Hera is always the link between all these and ground. So this is requires a lot of coordination on ground and in space. So we're working on that to achieve these goals. And yeah, our highest priority in the operations is to build a robust and safe way of operating Hera, because any failure that we will see at the asteroid will cause delays and would result in us getting not as close as we want to get to the asteroid. But this is one of our main objectives, so we try our best to make this the safest approach and operations as we can. Thank you very much.
Thank you very much, Hera Spacecraft Operations Manager Chalian Gerbuz. We now get to, I think, probably what we've all been waiting for, and that is a first look at the images. And I would like to begin by asking Dr. Stefan Ulemesh to come up. Stefan is with DLR and will present the image or images coming from AFC, the asteroid framing camera.
Exactly.
Good morning, also from my side. We had a very exciting night yesterday, waiting for the images to arrive, and actually we got splendid images of both Deimos and Mars during the flyby. So maybe we can show these images because, yeah, we see here. So. I mean, what should I say? The image. So what you of course know what you're seeing here is the Mars background and the dark Deimos just in front of Mars right here. This image has been taken around closest approach to Deimos. That was a little bit before closest approach to Mars. So it has been taken about 1,000 kilometers away from Deimos. That means a pixel resolution in the 100-meter range right here. What you also see is Mars is bright as compared to Deimos, the Martian moon. Some of you may be aware that the origin of the Martian moons is still a matter of debate because the moons, both of them, Phobos and Deimos, are very dark, reminding a little bit to primitive asteroids. So some people believe they are captured asteroids, but this is also from a dynamical point of view not easy to explain. Some others believe they are ejecta from a huge impact, but then of course the spectra are not easy to explain. And we learn a bit more now by this mission in preparation to other missions like MMX to be launched to explicitly investigate Phobos and Deimos. Now, this image you see here is also of particular interest because it's one of the very, very few images we have now from the far side of Deimos. So most spacecraft observing Mars, they are inside the orbit of Deimos. So we have some nice images from the side facing Mars, but this is one of the very rare and I think maybe of the best resolution we have so far of the far side of Deimos. So if we can go to the next one, this is now a movie showing you a sequence of images taken around closest approach. So I think they start with a distance of about 1,100 kilometers to 950 or so, and you see Deimos moving in front of the Martian disk. All of this taken with the asteroid framing camera. Developed by Optronics. You will see later on images that look a bit similar but are in a different frequency range. This is in the visible monochromatic, and if we go to the next one, I think we have one with color. No, not AFC. That's hyperspectral images, so that's going to be the next time. Okay, thank you. Did I say something completely wrong?
As always. No, I just want to acknowledge two people who did these images. Jean-Baptiste Vincent, who is the lead of the asteroid framing camera and worked hard last night, as well as Gabor Kovacs. So both of them worked very hard to get these images, so I think we owe them that.
Yes.
And I also want to acknowledge the HOPE mission by the Emirates that also did image of the far side, different phase angles. So we'll have a great synergy between at least three missions, HOPE with Emirates, JAXA mission, MMX, and Hera that also shows international cooperation at work. But I wanted also to acknowledge
Yeah.
Jean-Baptiste Vincent and Gabor
that's
Kovacs.
very
That's very important.
Thank you very much, Stéphane Ulemesh from DLR, and I would like to ask Marcel Popescu from the University of Craiova to come up and talk us through that fabulous blue image that we just saw a quick shot on. Thanks.
Good morning. So I am responsible for the HyperScout instrument. I'm sharing my responsibility with Dr. Julia de Leon from Instituto de Astrofísica de Canarias. I will tell you why we need to be two for this instrument. So first of all, let me report a bit of this wonderful image. Everybody knows that Mars is blue. So the Mars flyby, the operation yesterday, represented a good opportunity to test and validate our instrument in space, as exactly it will work at the asteroid. But it was also a great opportunity to explore Deimos at wavelengths where it was never seen before. So let me tell you a few things about this cutting-edge instrument produced by the Cosine. It is both an imager, that's why I have an image to present here and not a silly graph with some curves showing around, so we can take images, but it's also a spectrograph. What means it is a spectrograph? We can get spectral signatures of rocks and minerals and understand the composition of the surfaces we are seeing. So the color we are showing here is blue, just because the instrument doesn't work in the visible wavelength range. It works in the near-infrared wavelength range. It goes from 650 to 950 nanometers, so it's got a bit of red. What is red is now here colored, mapped as blue, and the red wavelengths are corresponding to the near-infrared, to the 900 nanometers. The aim of this instrument is, when we arrive at the asteroid, at the Didymos Dimorphos system, to get its composition, to see the minerals. It will be a first time when we will see inside an asteroid because of the crater made by DART on the Dimorphos, on the secondary asteroid. So we will try to understand what is its origin, what are the events that took place on this asteroid, Didymos Dimorphos, across all along its history, and to understand this object, because if you want to deflect an asteroid, first of all, you need to understand it, what it's made of. So, coming back to the successful test we had yesterday, we are very happy when we saw this image. This image looks perfectly as we predicted, and I want to thank here to the ESOC people that really succeed to bring the orbit and to bring this high-resolution image. We were able to get Deimos in front of it, so we will see this far side of Deimos. We will be able to characterize it, and we will be able to complement it with other data that exist in order to understand its properties, and why not, to put another piece of puzzle to understand its origin. This is the image we have to show you. It's a beautiful image with a wide field of view of HyperScout. It's 15 by 5 by 9 degrees. I think one of the highest field of view instrument. Let me show you also close by image to Mars. The next one image, please. Oh, so we have only one image. Please follow up on the latest stages, and we will present more and more images. Last but not least, I want to thank to the whole team, Julia, Gabor, George Prodan, Björn Geiger, who helped us to prepare all this image, and of course all the team of the Hera, who always provided us very useful info. Thank you.
Thanks. Thank you very much, Marcel Popescu. And what we're presenting for you this morning are the images that just came in as of 4:30 this morning, which is just a selection. The rest of the images and the data will be available via the ESA website, I think within the course of today. Before we move on to the TIRI instrument, I would just like to mention we are also, there are some journalists participating in this presser via WebEx. And if you have any questions and you're participating remotely, simply type your questions into the chat and we'll capture those to be asked here in the room. Good, I would then like to ask Tatsu Okada-san from JAXA, the Institute of Space and Astronautical Science, to come up and talk us through the TIRI, the hot TIRI images.
Thank you very much. I'm very happy to be here to provide the images of the TIRI, thermal infrared imager. Actually, I'm here on behalf of the JAXA and the Japanese colleagues, and also in collaboration with the Belgian team, especially for the Royal Observatory of Belgium and the VITO, especially for the very hardworking of the Oscar and Greg here. So this is the image of the Deimos in front of Mars. Actually, contrary to the AFC images, the Deimos is brighter. This is because the Deimos is higher temperature than the surface of Mars. This is because the Mars has cold atmosphere, so the surface is cooled. But the Deimos has no atmosphere, so the surface is hot. That is reflected, and also reflect the surface thermal physical property. So the investigating the surface temperature, we can obtain the surface physical property. That's a very, very good data, I think. So the next, please. Oh, this is a moving. Deimos moving on there. Yeah. Actually, the Deimos is brighter than the surface of Mars, and the Mars, the surface geology is also clearly imaged by the thermal imager. This is somewhat different from the visible light. So comparing the visible light FC and the hyperscatter images and the TD images, we can get more scientific information. So that's a very fantastic moment, and thank you very much for the comment.
Thank you very much, Tatsu Okada-san from JAXA. I would now like to ask Monica Lazarin from the University of Padua to come up and talk us a little bit through a couple of really hot planetary defense topics. Yeah. Monica.
Good morning, everybody. So while Hera is successfully flying towards Didymos, ESA is developing its second planetary defense mission to another near-Earth asteroid, which is Apophis. Apophis is in particular a potential hazardous asteroid. It's a big asteroid, 350 meters of diameter, that will have a close encounter with the Earth on the 13th of April 2029. It is a Friday, 13. So. And it will arrive at 32,000 kilometers from the Earth, so really very close. And it is 1/10 of the lunar distance. So this very close encounter with the Earth represents an unprecedented and very rare event, once every thousands of years. So a great opportunity for asteroid science and planetary defense. So in the last few years, we did a lot of things with asteroids. We deviated an orbit of an asteroid, We obtained some material from, we extracted material from an asteroid and brought it to the Earth. And now we have a great opportunity to see an object subject to a natural experiment. Very likely, there will be very strong tidal forces that will be exerted on this object, and with very important consequences on its properties, like the orbit for sure, the rotational state, the internal structure. There will be seismic waves probably, and also some rearrangements on the surface. So a really great opportunity, and it is close in our garden, this object. And it will also be a great opportunity also for general public, because it will be visible with naked eyes for about 2 billion of people in Europe, North Africa, and Asia. And so it is a great opportunity also for outreach. And we must also remember that 2029 has been declared the International Year of Asteroid Awareness and Planetary Defense. So you will have a lot of work also for the media. At this moment, we have only one mission which has been approved to encounter Apophis, which is the extension of OSIRIS-REx. It is called OSIRIS-APEX, but it will arrive only 2 or 3 weeks after the close encounter. So it will be able to study the properties of the object only after the close encounter. Instead, Ramses will rendezvous with the Apophis starting from 2 months before the closest approach, and so it will be able to characterize the properties of this object before, during, and after the closest encounter, so while they are happening. So this is really very important. And this is also another opportunity for international collaboration, as we successfully experienced with DART and Hera. Instead, we are already collaborating with NASA and also with JAXA. They are giving us the camera, the thermal camera, that is the similar one on board Hera. Then maybe the launch vehicle, we are discussing about it, and the light solar array. And we have to save money and cost and time, because the time available before launch is very, very limited. We will use the same Hera as a heritage for the satellite, the 2 CubeSats, and some of the payload. And so we will have the asteroid framing cameras that you have already seen, the 2 CubeSats, and maybe one of them will land on the asteroid, so carrying a gravimeter and a seismometer, and also TIRI and some other payloads that we are discussing. The launch window is 20 days starting from April 2028. And so we now are waiting for the formal approval by the ministerial, during the Ministerial Council in 2025. Thank you.
Thank you very much, Monica Lerzin from the University of Padua, for that overview on the Ramses mission. I would now like to ask Richard Moselle, who is our Planetary Defense Officer here at ESA and head of our Planetary Defense Office, to come on stage and give us a quick summary.
Hello. So as some of you might have heard, recently we were reminded of the need to be on the lookout for asteroids by a little fella called 2024 YR4. This is a sequence done by our by our telescope operators. So it has been discovered at the end of last year, 27th of December, quickly rose to more than 1% of impact probability, which triggered for the first time ever the International Asteroid Warning Network that is in place since about 10 years. And this was the first time that the warning network was activated and reported to the United Nations about an asteroid crossing the threshold of 1% with a diameter of more than 10 meters. So this was quite exciting. So this guy caused some work for us. And it even didn't stop there, because 1 month later, after discovery, or let's say 1.5 months later, it even rose to an impact probability of 2.8 according to our systems, or even slightly above 3% in the NASA systems. And this marks a new record in impact probability for an asteroid. It even surpassed the previous record done by asteroid Apophis in 2004. So this was really getting interesting and exciting. However, recently, I think just last weekend, it was possible to completely rule out any impact of this asteroid for the next 100 years plus. So while there is no danger anymore for Earth, for the Moon it seems to be going the other way. So the impact probability for the Moon is well above 1%. It's hovering around 2%. Latest measurements done by JWST, astrometric measurements, indicate that it might even go further up. So this will be a close one for the Moon. Stay tuned for more. We will likely only be able to decide this in 2028. So there's some work to be done. What this reminds of is that we need all the components of a planetary defense system. We need to have sky surveys which catch these asteroids early. We need to have a worldwide coordinated follow-up, as was done by I1. It coordinated our efforts, the NASA efforts, and that of all the other space agencies and participants in the network, which are plenty of. And also the possibility to evaluate this data. It's called assessment. And last but not least, the possibility to formulate reactions to this, which we also did in this context. It followed a pattern that I think it's worthwhile pointing out here, because we will see this more often. We will have more surveys in the future, and that means that we will discover asteroids at a higher rate, and surveys alone cannot give the precision to rule out or confirm impacts by themselves. So what we will see very often is something like this, where it starts out at below 1%, but at some point eventually it might hit 1%, and this is where we activate the International Asteroid Warning Network. We did it here. And then the impact probability will continue to rise slightly. We will see more cases of that happening. It's as the uncertainty shrinks, while Earth is still in the uncertainty region, it means that the relative size of Earth gets bigger, and that in turn means a higher impact risk. But eventually, when it's just highest, it will drop and drop in most cases. This last line marks when the International Asteroid Warning Network sent the all clear or the stand down message. So I'm very happy to announce that we are tirelessly working on improving capabilities. Just yesterday, the left image is just from yesterday, where our first Fly-Eye telescope of the network saw the sky for the first time. It's not yet switched on. We just aired it a little bit and showed it around. But soon, as the artist depiction on the right shows, it's supposed to first go through commissioning in Matera at an ASI site, but then go up to Monte Mufara in Sicily and perform its duty there. And in turn, it will be joined by 2 or 3 siblings. And the idea is, as Holger pointed out, to observe the entire visible night sky around Earth within 48 hours to a depth of 21 magnitudes. But we won't stop there, because we still have a blaringly obvious blind spot. It's if you look up in the bright sky, you will not be able to see any asteroid there. Something like Chelyabinsk could happen any moment right now. We wouldn't have any pre-warning. The pre-warning would be the time from flash to hearing it. But rest assured that we are all working on this in the international planetary defense community, while NASA is getting ready to launch their NEO surveyor mission. We are building the first dedicated early warning system in space, NEOMIR, Near Earth Object Mission in the Infrared. It's a working title. But this satellite will be deposited between Earth and Sun at the so-called Lagrange 1 point and do rapid scans around the Sun to scan the inner solar system for asteroids. There are asteroids up to 1 kilometer and more that we have never observed before. So I'm really excited for this mission, which will be the next planetary defense cornerstone mission after Ramses has done its job on asteroid Apophis. So I hope I could convince you that we are not at the end. We are not arrived, but we are only at the beginning. And Hera is an amazing first step in this direction. I'm so happy everything went well. Thank you very much.
Thank you, Richard Moselle, Planetary Defense Officer here at ESA. Before we move into our Q&A session, I would just like to see if Ian wants to come on stage, Ian Carnelli, our mission manager, and give us a quick demo of an exceptionally cool product.
Thanks, Daniel. What's cooler than Hera, right? Good morning. So I'm Ian Carnelli. I'm the Hera mission manager, and I have the privilege of closing this session. And my first words are, of course, I have to thank the teams who have worked on this tirelessly on this project. And I'm going to get very emotional because they make it look easy. They make it look very easy, but the truth is that the amount of work that has gone into this project is beyond imagination. And the dedication of everybody, the scientists, the industry, the engineering team, has been absolutely amazing. This is a very innovative mission. We are trying, as you heard this morning, we've tried new techniques in navigation. We're trying new science approaches. We're going to do incredible science, and this is just the beginning. So a mission to defend Earth from asteroids, bringing possibly a dinosaur with them, and do this fantastic science is something that engages the public. So we want to engage the public in a new way, and we're also starting to test new ways for this. And I want to give you a preview this morning because we are launching a Hera companion. It's an AI-based application. For the first time, you will be able to access live telemetry, near live telemetry, from the satellite, ask where the satellite is, interact with the satellite, and access the images and do a lot of things. And this can be done. The amazing thing is that it will talk to you even if you are an astrophysicist or are 6 years old, and will adapt the kind of questions and the interaction you have. So we try new things. Not always they work. So this is the first live attempt, and I would like to demo this to you. So this project has been done with Terra Mater Studios, Impact AI, and Microsoft. And it's not been easy, so I want to bear with me and see, and let's see if it works live for the first time. So hello, Hera.
Greetings, Earth Explorer. I'm Hera, your space companion. I just had an exhilarating flyby past Mars. What's on your cosmic mind today?
Well, you know, I'm in front of all the journalists, all the scientists, so I feel a bit emotional, and we're presenting the first images you took last night.
Here's a breathtaking image I captured of Mars using my asteroid framing camera. You can see the red planet in stunning detail, giving us a sense of its grandeur and mysterious beauty. It's thrilling to share this with you and the team.
So
imagine the
how
discoveries
did you
that
feel
await
when
us
you
as we
flew by
journey onward.
Mars? Yeah, I know. They don't like interruptions. Let me see. So how was flying by Mars?
Flying by Mars was an unforgettable experience. In this image, you can see Mars as I captured it. The flyby was more than just a breathtaking sight. It was a vital part of my journey. I adjusted my trajectory to get close to Deimos, Mars's smaller moon. My instruments got to work, capturing invaluable scientific data. It was like a cosmic postcard from Mars.
And can you tell me how's your telemetry right now? Is it looking good?
Here's a snapshot of my recent telemetry data. Angular velocity. Reaction wheels are spinning smoothly, maintaining stability. Attitude vector. Holding a steady orientation in space. Commons. All instructions from Earth are executed efficiently. CPU. Operating at a comfortable level.
Hera.
Standing by for the next big move. Reaction thrusters.
I don't like
Ready
you.
for precise attitude control. Temperature current.
Can I interrupt you a second?
Of course. What's on your mind?
Can you tell me a joke about Deimos?
Sure. Why did Deimos invite Phobos to the party? Because it knew Phobos would bring a moon-tastic time.
That's awesome. So, last question to you, Hera. How did it feel seeing Mars after many months in deep space in the void?
It was truly awe-inspiring. After months in the vastness of space, seeing Mars up close was like reuniting with an old friend. The vibrant reds and the mysterious moons are a sight to behold. It filled me with a sense of wonder and renewed excitement for the journey ahead.
Okay, we'll stop it here. But I hope you got a feeling of the potential of this tool. And I invite you today, we're releasing at 1 o'clock the voice interaction. The chat is already available, but the voice makes it a completely new environment. And this is just the beginning. You're going to be able to access more and more data. You can ask any scientific questions, or you can ask jokes as you've seen. So I hope you will like it. And it's Hera.space. And if you create your own account, then it remembers who you are, and you can get a very good experience. Yeah, she talks a lot. All right, so again, I want to thank you all. It was a very, very short night. The scientists have worked literally until 2:30 in the morning, and the excitement was such that we didn't get any sleep, and probably you can see from our faces this morning. And I'm really, really thankful to all of you, because you made this mission very special, and it's been 20 years in the making. And today, it's your day. Thank you so much.
Thank you, Ian. Good. We want to go into our Q&A phase now. And just before we begin that, I would just ask a number of people to identify themselves. So if you're a Hera scientist, would you please raise your hand? Okay, these are the scientists. There. Good. There at the back. If you're part of the Hera flight control team, mission control team. There. Also, Pablo, yeah, of course. We don't get anywhere without mission analysis. Part of our planetary defense office is Richard, and I think we have Juan Louis. Planetary defense. Our space safety program, I see Holger, and I think we can talk to you about space safety. So our mission operations, I see Simon Plum, head of mission operations here at ESA, responsible for all of our missions that we fly anywhere, not just Hera. And yes, with that, I would definitely like to open it up for Q&A. And we have microphones here. We can toss over to you or bring over to you. And if you have a question, please just go ahead and raise your hand.
Yes. Hello. Uwe Gerz from Hessenschau.de. I have two questions, actually. First of all, you mentioned that this flyby maneuver gets you information that brings you closer to the answer of the origin of Deimos and Phobos. So can you already tell in which direction the findings point? Is it rather an asteroid, or is it... you keep laughing. And the next question would be, in the visual image of Deimos, it appeared to me that the surface looked pretty even. Is that owed to the resolution of the image, or is it has it something to do with the surface of the moon?
Michel Kuipers.
So I can take the first one. The short answer is no. At this point, we haven't really reduced the data to the point that we could say something about the nature of Phobos. Now we hope, especially with the spectral information that we have and that is new, that we get new information about Phobos that also may give hints. Sorry? Deimos was a long day. about Deimos that will help to, that will feed into the discussion of the origin. I wouldn't go to the statement that we will solve the problem. I think we cannot go so far. And maybe Stefan can answer the second question.
Talk to that? Yeah, okay. Well, one reason it looks so smooth is due to the phase angle. So you see, we have the sun in the back right now, and also if you look at the full moon, it looks smoother than if you look near to the terminator. And that's a reason why it looks very smooth right here, because we have the illumination basically from the side of the spacecraft.
Directly onto it, yeah, okay.
No shadows, that's what it means.
Okay, thank you.
But it doesn't mean it's smooth and cozy.
Maybe we can just recall for the origin, we'll have the MMX mission by JAXA that will go and take a sample of Phobos getting back to Earth. However, they will also do flybys of Deimos. And I think the great thing with Hera's flyby that we can combine the data of Deimos flyby by Hera with the one of JAXA, MMX, and also the HOPE missions, so that we have an understanding not only on Phobos when we get the sample, but also on Deimos, because we need to explain both in one scenario. So it will be very complementary to all other data that we get from it.
Thank you. Next question.
Good morning, Robert Vogel, Paris Magazine. I have a question about flight trajectory in general. So who decides about the flight plan? Do you choose the easiest way, the shortest way, or the interesting way, as we see now for the flyby through Deimos? Who decides this?
Yeah, so, okay, we start, of course, with the optimal trajectory in terms of fuel, so we want to minimize fuel consumption. But then we saw there was this opportunity that we were passing close by the orbit of Deimos. We needed to adjust still the flyby altitude, so the Mars swim by altitude, to really pass very close. And we also had to change the time of the swim by, such that Deimos would be at the right time. And this implied a penalty in fuel. So we went away from the optimal just to have this observation. But let's say the baseline start is always optimal fuel trajectory-wise, or sometimes you also want to minimize time. So actually, that's the case of Hera. For this launch date in 2024, since we had the opportunity to perform the Mars swim by, we could save a lot of fuel, and then we could advance the arrival to the asteroid system. So then we can extend or have more beneficial mission duration. So basically, these are the elements you have to trade, but it's done on a case-by-case basis.
Thank you, Pablo. Next question. And if there are no more questions in the room, I will share one question coming from one of our journalists joining via WebEx, Leo Enright in Ireland. And he is asking, are we seeing what Stuck et al. Call the trailing hemisphere of Deimos? Will you be able to pull much more out of the topography? And maybe that's... It's for Patrick.
Oh, okay. We see the opposite side from Mars of Deimos. And in terms of topography, well, we have to see, we see some features on the images, but we just downloaded them, so we have to analyze them further in order to really understand what we see. So I would say it's a little early to say more about the topography, but we will work on it.
And about trailing versus leading, if I get the geometry right in my head, we see kind of half the leading and half of the trailing at the hemisphere of Deimos, because we are looking at the opposite side from us.
here you see both, of course, the trading and the leading. And you're not supposed to ask this. I think it's going this direction. So this is the leading one. This is the trailing one. And okay, I said you shouldn't ask this question. Yeah, exactly.
Okay, I think that was sort of answered.
So Brian will answer the next question.
Brian will answer the next question. Speaking of Brian, actually, if you tap him on the shoulder, he's doing some really interesting work with stereoscopic images, and he may be able to show you a kind of a cool demo. I think that's pretty much, we're almost at the end of our formal, Sean's pointing at his watch.
Just to remind about the midday.
Thank you very much, yes. What we'll do now is we'll wrap up. I'll ask Simona to jump in. Of course, we are going, what we'll do here at ESA is we'll go live with our webcast at 12 o'clock. That will be via the ESA YouTube channel. We'll present these same images, and we have some very, very cool guests coming into that webcast, including ESA astronaut Alex Gerst and a sci-fi author named Andy Weir, who wrote The Martian. So we thought it would be great to bring him in and celebrate with us going past the moon. In terms of your needs here in the room, you are welcome to now tap anybody on the shoulder that you want to talk to. Simona Nishteanu can loop with her. We can definitely take you to the MCR if that's what you wish. She's nodding, so that's a yes. You can do your interview here if you want. And of course, Brian wants to do a.
Well, I'm only going to say it's here if anybody wants to see this in stereo.
Come and see Brian. We'll all be here now for a little while, so don't hesitate to talk to any of the experts. We'll publish images at 12 noon and a full news report with captions, and the rest of the images we'll be able to email to our media list within the day. So I think we're covered. So with that, I would like to say thank you very much. I'd like to thank everybody who worked on organizing our press conference this morning. Thank you very much. Thank you to Simona. Thank you to the communication team here at ESOC, and also thank you to our FM colleagues who set up a fantastic briefing. And with that, we will call it quits. Thank you very much.